Exploitation. It's being recorded. So today's agenda, first we're going to talk a little bit about memory and how it's laid out in your computer. And we'll also lead you through a little bit of an introduction on buffer overflow before the attack lab is released. And we'll also give you a demo and a little bit of a demo on GDB, or a demo on buffer overflow in GDB. So first, what does memory look like? So we allocate memory through the stack and the heap. The stack is for local variables, like variables that aren't dynamically allocated, whereas the heap is for dynamically allocated variables, which is when you use like keywords like new and delete in C++, or yeah. So the stack starts at a high address, which you can see up there, and it goes down. So the top of the stack will actually be at a lower address than the bottom of it. And while the heap starts at a low address and grows up. So everything in memory has an address. So you can go to a function through its address if you can find it in GDB, which I think Steph might show you later. So first, the stack. So just like you learned in CS32, the stack is the last in, first out data structure, sort of like a stack of plates, where the most recently added thing to the stack is going to be on the top. And when you take something off of the stack, like when you pop it off, you'll access the most recently added one. So anything in the stack is automatically allocated and deallocated by the compiler. So you don't have to do anything like deleting it or like worrying about memory leaks. Like the compiler will do it for you. And there's a stack pointer that will point to the top element in the stack, RSP. And you can use that to like grow and string the stack. So how is memory laid out on the stack? So when the compiler wants to allocate memory on the stack, it'll do so in stack frames, which you can see right here. And stack frames are just big chunks of memory that are allocated every single time that the compiler wants to add something to the stack and that it doesn't have the memory for. So it contains the parameters for the function that it's about to call, the local variables that it can't keep in the registers, and the return address for the function. So these are used in recursion calls. Like this is the thing in languages that use recursion. So like you can call a function and then call it itself again, and it'll create a new stack frame that'll save like the parameters that you're getting to the callee function. And like you can kind of go back sort of like you can return values to like the earliest stack frame. So some ways that like the stack, some operations on the stack are push and pop, which are very much so like the data structure. Push and pop, when you push something onto the stack, it literally just gets the value at that it's pushing onto the stack and puts it on the stack, and pops off the top element of the stack. So while the stack is laid out like in a very organized way in memory, the heap is allocated in sort of like a random manner. It's basically, like I said before, for dynamically allocated variables. And because the programmer allocates and deallocates anything in the heap, you have to be very careful about memory leaks, which can happen if you forget to delete something that was allocated onto the heap. And that can lead to some interesting program behavior, especially when the memory gets all used up. So that actually brings me to the focus of this workshop, which is buffer overflow. So before I talk about buffer overflow, let me define what a buffer is. A buffer is just any segment, well-defined segment in memory used to store data. So this can be like your arrays, your strings, just like anything that has like a set amount of memory allocated for it. So they have specific sizes, And you can exploit this in something that we call buffer overflow, where say you have like an array of size 10, like 10 characters. So that means that you allocate 10 bytes for it. If you were to write an input that is, say, like 20 bytes long, you could cause a buffer overflow to happen. And you can see like in the meme, if you have a buffer overflow vulnerability in your code, if you type in something very long that the program can't handle, like functions like gets, it will cause some interesting behavior. And it's very cool. There's many things I'm sure Benjamin will show you. So a little, okay. Anyway, so there's two types of buffer overflows that can happen. The one that we talk about in CS32 is actually Stack Overflow, which you might be like, whoa, that's where the website gets its name. And it's yeah, so, but the other type is heap overflow, and it's not as common, but it happens when memory is corrupted on the heap. And this, you can do this, you can accomplish this in a few ways. One of them is like through memory leaks, where you just keep on using the memory and then eventually it doesn't have any memory left that you can allocate. So, you can corrupt the data on the stack, or not the stack, the heap in that way. And like I was saying before, Stack Overflow is the other type, and it's so common that they call it vanilla buffer overflow. So this will be your stack smashing, which is what we'll do in the attack lab. And the most common form of this is where you have user input. And because stack frames, the stack is allocated in frames, memory is finite. So you can take advantage of that by inputting more data than the amount of memory that you have allocated. So you can corrupt the data on the stack in that way, and cause code that shouldn't be executed to be executed. So.
All right, so we'll now be going over some examples of buffer overflow real quick. Oh, there's many questions in the chat before moving. Oh, okay, good. With that, let me start sharing my terminal. Oh. A little better? Can everyone see that better? All right. So I'm just going to log on to my CSNet account real quick. All right, and we're going to go into this folder. I have a couple of examples in preparation for this. So let's start by looking at this first program over here, main.c. All right, and let's take a look exactly what this is doing. It's a pretty standard program. It's sort of like your sort of password protection program, where it takes an input of a password, compares it to what the password actually is. In this case, I set it to ACM Cyber, and if checks that to see if it matches, and then determines whether or not it passes so that it can output the flag or the secret message. So let's take a look at that real quick in action. All right. We run main. If we type in, just say, an arbitrary password, someone give me some random phrase. Password, the best password in the world. Oh, it's the wrong password. Sorry. So let's try what I know to be the actual password, which is ACM Cyber. And of course, that works to give us the normal flag. So normally, you typically would think that only knowing the password would be the only way to exploit this program, right? The only way to get the particular message. Well, as we just learned about buffer overflow, what you actually can do is you can overflow the buffer and actually cause a segmentation fault to get the password. So let's see that in action real quick. So if we go here, and if we just scream really loudly with a long input, what we do is we can cause a segmentation fault and we still get the secret message. So let's now analyze for a second, why exactly does that work? So if we go back to the program a little bit, so how exactly did I write this program to check for the password? So the key things to look at here are gets and string compare. So if you guys aren't too familiar with writing in C, what gets does is that it writes from standard input onto an allocated buffer. So in this case, we defined a buffer called buff to be a size of 15, and get simply writes in what we input to that particular buffer. However, since we allocated a specific size of the buffer, then if we overwrite that, then we start allocating into memory on the stack that we did not allocate specifically for that buffer, and we can cause some error. And another key thing is the string compare. So string compare is a C function that compares what's in the variable. It compares just two strings. So it would compare the C string of buffer with the string ACM cyber. And if they are the same, then it will return 0, which is why I'll go to correct password. That's why correct password is an else. And it returns anything else, then it'll return 1. Because string compare, what it does, it returns sort of like the differences between two string variables based on the character encoding. So let's also take a look at what the assembly code looks like for this. So we're going to use a common program. So if you came to the workshop last week, we talked about both static and dynamic analysis. Dynamic analysis being when you run the program to analyze it, and static analysis, which is what we're going to do now to look at the program while it's not running. You can use the obj dump and with the flag of -d on the program main. And if we take a scroll up through the assembly to the main function, what am I looking for here? I'm looking for 2 key checks for jump. So as you can check, as you can sort of check here, the key thing is the jump equals and right here. So the jump equals is, if you remember back to the program, the comparison with the value of string compare, right? Because the call of string compare determines whether or not it's 0 and returns that. So as you can kind of look at the assembly program here, if you take a look at key parts, let's take a look at, say, LEA. LEA is a key program here, key command here, because this defines the size of the stack frame, right? If you remember back to the program, we allocated a specific buffer size, and what the stack frame does is that it takes that buffer and fits it onto the stack. So RBP being the base pointer, right? It grows the stack downwards instead of 20 in hex, which is 32 bytes. So it allocates 32 bytes on the stack from the base pointer to allow the input. And once we overflow that, we could then write to somewhere else. Now, another key instruction to look here is this move L over here, which moves onto 4 bytes from the base pointer of the stack, the value of 0. So if you remember back to the C program, I initialized the value of pass, which is like the check for what you use to see if you're logged in, to be 0. And so that's what it does. So basically what the visualization on the stack is right now is that from the base pointer, there's the integer for checking for whether or not it's the 1 or 0, right? To check if whether or not the password logged in. And then 32 bytes from the base pointer is the buffer we allocated within the stack frame. So what we do is that if we overwrite the entire size of the buffer and overflow into the 4 below the stack base pointer, what we're doing is that we're overwriting the value on the stack through the buffer into the value of the integer. So if we then take a look at string compare, which then says, okay, if we look at like, if you know Booleans in C, it's the Booleans is true if it's any other value and false if it's 0. So with string compare being any other value, it runs true, which causes the segmentation fault and then causes the output of the flag because the pass check is true. Just to sort of clarify a little bit, I'll open up the C program again. As you can see here, because we overwrote the buffer, this changed the value of pass to some arbitrary value based on what we overwrote. And because of this, this becomes true, and this runs this particular program for segment faulting and returning 0. So that's how we're able to exploit this program. If anyone has any questions at any time, feel free to interrupt me. Oh, that is an interesting question. Let's try that. I did not think about that. I was going to try it again. Actually, what would this be represented as? I'm curious. Oh, wait, that's not enough. Oh, right. It'd be the string version of this long thing. So no matter what, it was still a segment fault still. So if we were hypothetically able to write it into just the value of 0, then I think the check will fail. Right. So that does make sense. Good question. All right. Now let's take a look at this next program. So number.c. So just to sort of summarize what this program is it takes two input values it prompts you for two input values of two integer numbers. And it's asking you then to make sure the two numbers sum to a negative number. However, the one restriction that you have is that neither of the numbers can be below 0. So you're trying to add two positive numbers to become negative. So how is this possible? Does anyone have a guess? Sorry? Right, in max. So basically, we can do something with integer overflow here, right? So in this computer architecture, integers are 8 bits, 8 bytes, right, long. And so when you represent them, right, there is a maximum number that they can represent. And so once you go over that particular value, it overflows and becomes negative. So that's what we're going to try to do here. I'm just going to arbitrarily type in value, unless someone remembers int max off the top of their head. Yeah, all right. I'll just do this and hopefully, wow, wrong program. Let's go. I'll just arbitrarily make a big number. Hopefully this number doesn't overflow as well. Now we'll just try it again. Okay, there we go. So as you can see, we added two very big numbers, yet we're able to make a negative number still because of overflow. Now, this is like a pretty simple example of overflow. Why did I decide to show this? Well, the reason is this sort of shows you the general approach of how to deal with these buffer overflow type problems. You have to start with understanding how the memory layout sort of is for the particular kind of structure. In this particular case, you just understand how integer is represented in this particular architecture. In the previous problem, you had needed to understand how the stack layout was formed with a particular buffer aligning with the next integer variable aligned right after that. And this allows you then to manipulate the programs in desired ways, which we'll see in this next example over here, because you understand the particular layout of the program. So just to add another example, let's say if you wanted to hypothetically, access values within like a 3D array or something in C, and you don't have the ability to, I don't know, there's some arbitrary limit preventing you. Well, you can still, if you understand like the structure of the 3D array, you can do specific kinds of input manipulation to then able to access parts of the 2D array, the 3D array. The reason I'm mentioning is there may be a challenge on this on acmcyber.com after. But with that, we're going to then see the coolest, in my opinion, implementation of, oh, do we have a question? Oh, okay, thank you, Jerry. We're going to then see the coolest implementation of buffer overflow here. So if you take a look at this program, this is an even simpler program. If you look at the main function, it's literally just one function called to echo. And all echo does is that it creates a buffer, with, size 20. It, prints out some text prompting you to add, something to the buffer, and then copies what you put in there. Now, what's also in this program is there is a secret function in here. Now, if you look at this program right now, there's literally no call to this whatsoever, right? So you would think that in a typical programming sense, it will be impossible to call the particular function. Well, actually with buffer overflow, you are able to call the function even without changing any of the C source code. So let's try to do that right now. So let's just, of course, test the program itself. Let's run both. Anyone want to type in a secret message or cool message? Bueller. PBR, let's go. See, it just copies out what you're putting in. But of course, if you try a buffer overflow, let's try it again. This probably should be good enough. It causes a segmentation fault. Now, this is pretty good, but we're not able to run the call we wanted, right? It's still segment fault, which is, okay, we kind of understand that's how buffer overflow is writing to a part of memory that we didn't design within the stack frame. But how do we get the particular function call? Well, we'll have to then understand sort of what exactly is going on within like what's the layout of memory? What's the layout on the stack at this point in time? And let's do some more static analysis for that. So if we take a look at the object dump, let's scroll up to main, you can see the call queue to echo. And if we look at echo, let's take a look at what's going on here. So the key assembly code to look at, which I mentioned kind of briefly before, is this LEA, which allocates this buffer size of 20, or in decimal, this is hex, so this would be 32. So it would be 32 below RBP. Now, RBP in itself is an additional 8 bytes. And if what happens is the 8 bytes above RBP is the instruction pointer, or where the program returns to after this particular function call. And so basically, if you overflow the bytes allocated right there in particular, overflow and overwrite RBP, well, then you could write to the next 8 bytes, the instruction pointer, what you want, basically. In this case, we want the call to secret function over there, which is this particular memory address over here. So let's try and do that right now. So a useful tool in these sort of problems is Python, because we all like keyboard spamming, but I don't think we want to sit here all day as I type in 40 different letter A's as we go here. So we're just going to use Python to help manipulate that a little bit. If I type here, can people still? Oh, people cannot see this. All right, let me just click on it. All right, there we go. So we're going to use Python to then write a little bit of output handling that sort of helps us here. So this is pretty useful if you want to say, do this in a particular, like for the attack lab or something like that, instead of maybe putting in a .txt file and putting that in standard output. So what we can do is we do Python print a, and what this does is we can actually multiply the inputs in Python by a certain number, let's say 20, and what we get is that this input done that like that. So with this in mind, what we have to do then is we have to then overflow the allocated buffer size, overflow and overwrite RBP, and then we have to write to the instruction pointer what exactly we want to do. So first, let's go back and take a look at object dump. Does anyone remember the value that is the size of the particular buffer? That's right, 32, because this in decimal is 32. And so we know then that let me just do that. And that we know then we have to then scream a minimum of 32. Now, the next thing, so that's the size of the buffer. The next thing after that is RBP, which, does anyone remember how many bytes a register pointer is? 8, exactly. So this becomes 40. And then the 8 bytes after that is then the particular address itself of the function we want to call. So if we scroll back to object dump, we can then take a look at the particular address you want to call, which is this over here. I'm just going to copy this. And what we then do is, if we go here and copy it, if we then sort of do this, then we're able to do the particular buffer overflow and call it. Now, there's one thing we still need to change over here. Does anyone remember something about how memory is sort of interpreted in x86-64? Something to do with endianness. Okay, I'll simplify the question. Is x86-64 big endian or little endian? Little endian. Okay, so that means we have to write this memory address in little endian form. So let's do that real quick. So x, this is how you format it into hex in Python. So 05 x 0540 x00. So if we do that, hopefully I did not mess up anywhere. This should hopefully run the secret function if we then pipe it into our program. And fingers crossed, there you have it. We have called our secret function that, if we look back to our C program, was impossible to call anywhere before. But how do we do that? We sort of understood the particular layout of the stack. So I'll just run through again very briefly with the slide I have on how exactly this worked. So, this was just a classic example of how stack smashing worked. So as you see, I kind of flipped upside down an earlier diagram, because even though this is the stack top is on the bottom because the stack goes downward. So that's a good way to remember it. So this example I gave was just an example of stack smashing, and going to how things are done. When a function is called, the first thing that is pushed onto the stack is the instruction pointer, so that the function call knows where to jump back to in the original program, so that after they finish the function call, they can just go back to the right place in the program. The next thing after that is RBP, which is the base pointer, so that it can reset the value afterwards and sort of keep the register value the same. And then it allocates the buffer size to make sure the stack frame is the right size it's needed. And after that, then it runs the sort of program. And then after it's sort of done with everything, it pops it off the stack. So what we did though, is we understood that RIP is there, RIP is here. No, RIP is here. Very confused. RIP is here, RBP is here, and then the data for the particular buffer is down here. So we wrote from the buffer going up for the 32 bytes. We then wrote 8 bytes more over RBP, and then we wrote then the last few bytes into the instruction pointer, so that we can give the particular function call that we want. So that is kind of cool. So hopefully that makes sense. Does anyone have any questions about that? That might be a little confusing. Yeah. Well, if we look back at this assembly program, that's actually interesting. Look at this program, it is. So I don't have a particular reason for that, unfortunately. As you can sort of tell you. This right, so for each particular function call of main and echo, and even secret function, we have it pushing onto RBP so that they can reset the value afterwards. Any other questions? I'll throw out a question myself because I may have done this really quickly. So anyone who might have noticed me type this, not have noticed me type this out really fast, may have noticed that when I type this out, this is not 8 bytes, right? The last 4 things are not 8 bytes. That's only 4 bytes, right? Does anyone have an idea on maybe why I only typed out 4 bytes? Right. Oh, sorry. Yeah, the rest is just zeros. So the rest of this address, if we want to make it completely full, is that it's just zeros. So 1, 2, 3, 4. So if we run this again, oh no, it does work. So, as you can tell, that it runs the secret function yet again, because this is the complete memory address. I just omitted some stuff. I just omitted the upper 4 bytes, and this is sort of just putting it into the lower half of the register. So that being said, even if you wanted to really, I added there was like a leading set of zeros here. If you even run it with like this per se, it still understands that the rest of the register is zeroed out, and that if you write to the lower 3 bytes of the 8-byte register, then it still runs the particular function that you want in memory. So, oh yeah, Rory.
Is that only the case if you're working with really low addresses though? Because if you're working with higher addresses, then you might overwrite like the first 3 bytes, but then there might be more bytes that have not zeros in them.
I think you're absolutely right. So, particularly with this example, it was very convenient that my compiler compiled this program into these very low byte addresses, so I could just start it right there. But let's say on the attack lab, you do your static analysis or dynamic analysis and realize that, oh, the particular function call is really high up on the stack somewhere. Then, well, actually, I think they will typically be on the lower addresses, because if you remember, instructions in assembly like belong in the text section of memory, and the text section is very, very low in the way memory is designed. So the stack is on the very top, right? It grows downward from there. But instructions like this particular address, which is, why there's a bunch of zeros in front of it, it's a very low address, are stored on the text section, which is on the very bottom, like towards the bottom of the memory addresses. So I think typically you might be able to there may be cases where there are higher addresses. So, don't, that's not set in stone, but of course, just do the static or dynamic analysis to find the particular address of the function call you want, and you will be able to, run these sort of programs in that sort of fashion. Any other questions about the demo? Okay. So with that, we're going to move back to the slides and talk about binary exploitation as a whole. So what exactly is binary exploitation? Well, it's this cybersecurity topic where a binary or an executable's program's vulnerabilities are taken advantage of to modify how the program functions. So this is not changing any of the source codes, it's changing, exploiting the function already prepackaged to figure out how it's sort of done. So this is also known as pawning, and there are a couple kinds of binary exploitation. One particular type is buffer overflow, which we went over earlier. Particularly a subset of buffer overflow, which is the most relevant to CS33, is stack smashing, which we just showed an example of just a second ago with the function call. And now I think a lot of people here are looking to how to practice binary exploitation outside of maybe their class or maybe this workshop. Well, I recommend just going to Google. There are surprisingly a lot of websites, typically starting with pawns, something like that, like PWN, and there's some name after that where you can get more binary exploitation practices, although they can get pretty hard. So, tread carefully. Or what you can do is you can write your own C code, like I did in preparation for this workshop. Now, one thing I will say, if you want to write your own C code, is that you have to know a couple things about the C compiler, which I just want to mention briefly. So C, of course, is a high performance language, but it's also a high vulnerability language, as the sort of very funny video that we have linked here if you want to take a look in your free time. It's coding in C until my program is unsafe. And as you can tell, the video lasts 42 seconds because the guy literally writes one line and then the video ends because, yeah, his program can get hacked. So, but that's good for us to practice this sort of stuff for binary exploitation, since we can write a program pretty easily and then figure out a way how to break it and exploit it. The one thing you will have to note, because the GCC C compiler has been pretty up to date with sort of basic stack smashing exploitations. So what you have to do something with the compiler, which I like to call killing the canary, by adding this particular flag. So the canary is this hardware implementation where the hardware architecture adds this particular number after a particular buffer. It's going to be a very small number, so that if the buffer is overwritten, the canary is sort of run over, and then the value of the canary changes, so that the computer sort of knows that, okay, there's overflow with a particular buffer. And basically what you have to do is you have to kill the canary by disabling this particular stack protection with the particular GCC, with the fno stack protector flag after running GCC. So I had to use that program while compiling the last program because otherwise I wasn't able to do that particular exploit. But once you do that, you should be able to write your own vulnerable C code, which we all want to do as software developers. So there you have it. That's binary exploitation. Oh, you can watch the video on your own time.
I'm just going to give you a quick demo on how you would look at these types of buffer overflow problems using GDB. This is just a review sheet that you can reference for certain commands that might be useful. But here, let's.
Oh, let me. You just type it. Yes.
Okay, so. Right, so I've created a code that basically, here, let's take a look at it. Oh, crap. Typing is hard. Basically, this code will create a buffer and a string. The string says don't lose the string, and it's going to be allocated as a local variable. And this buffer is going to be 64 bytes long. And I've also zeroed it out, and you'll see why later, so you can be able to see it in the stack. But basically, this program uses getS to fill the buffer. And as Benson explained, it's a very vulnerable function. So let's run this function and see what exactly it does. It just takes in an input, so we can put in literally anything. And then it'll write out, don't lose this string. So our goal is going to be to corrupt this string. So let's take a look at this in GDB. First, we're going to set a breakpoint at main so that we can walk through the instructions. And then we're going to run the code. Now we can use disassemble, which is kind of the same as object_dump, where you can look at the assembly. Here we see the string being pushed to the stack. You can try to translate it yourself, but believe me, that's the string, don't lose the string, being pushed onto the stack. And it's being pushed off of RBP, which is why we know it's being pushed onto the stack. And the same thing over here. This is where the buffer is being allocated and pushed onto the stack. And it's also being zeroed out. This is all the zeroing out of it. So let's continue on to where all of this has already been pushed to the stack. We could set a breakpoint there. We want it at 005 CF. And we press C for continue. Now we're here. And the best thing we can do now is take a look at the stack and what it looks like. So this is printing out the memory. And here we see our buffer. We can tell it's our buffer because it's completely zeroed out. And if you counted, there's 64 bytes. And then the string that we allocated is going to be right over here. You can also translate it, but I'm telling you it's the string that was allocated. And so it'll be right under the buffer. That means that to overwrite the string, to corrupt the string, we're gonna have to completely fill the buffer. Now, if you counted it, it's 64 bytes long. So all we need to do is input 64 bytes and then input the string we want to use to overwrite our own string. So we can quit GDB and take a look at an input. You can do this input with Python too, but I just have it already ready. Basically, there's 64 A's and then haha, you've been overflowed, which is just enough bytes to overwrite the string that was originally in memory. And so now if you run the program and you input that text, it'll print out haha, you've been overflowed instead of printing out don't lose the string. So essentially we've corrupted the string and overwritten it using buffer overflow. Yeah, that should be all, I think. Thank you. Do you have any questions?
All right, thank you, everyone. So if you want to stay connected with any of our socials, please check out our Discord, our Instagram, or or check out our website as well. So right now we have challenges available on our website at acmcyber.com related particularly with our challenge, particularly with our workshop. So if you want to check those out, feel free. Bills will stay up even after the workshop for a majority of the quarter. So if you want to attempt them at a different time as well, you can. And if you have any questions at any point in time, even after the workshop, on a particular challenge, you want a hint or something like that, or you want to check, whether you're on the right track, then feel free to DM any of the officers. The officer specifically who wrote the challenge will be on the particular challenge, so that if you want to DM them specifically, you can, to ask them a question about their challenge. So with that, thank you everyone for coming, and let's do the challenges.